Hello and welcome to our final project presentation for ECE 3710. My name is Kendall Draxler. I'm currently in my junior year studying electrical engineering here at Utah State University.
My name is Avery Stewart. I am also an electrical engineering student in my junior year at Utah State University. And for our final project, we decided to design a light tracking solar panel system. The reason for this is because a lot of systems that people use today have it set at a specific angle. And for our system, we designed it so that we could track where the light is so that we could optimize and maximize the amount of energy that is available.
Our solar panel will be able to follow the light and ensure that the angle is always the most optimal for whatever the sun is at during the day, and in turn producing more power. So now we're actually going to show you our design and the hardware for our light tracking solar panel system. All right, so this is our system for the light tracking solar panel. Right here is our actual solar panel system. We didn't use a real solar panel because we felt like that was a little bit out of the scope of our knowledge, so we built a mock solar panel out of cardboard to mimic what it would look like. Attached right here are our two light sensors. These are the things that are going to receive the input, and they send information to the board using I²C. These sensors have a built-in ADC converter, which receives the light, converts it to a digital signal, and then sends to the board. And that's how we're able to measure which light sensor is receiving more light, which then is fed over to the LCD right here.
Here we have the LCD screen wired up to the microcontroller. They are wired to the GPIO-B pins, which you can see over here. And so the purpose of the LCD screen is to display the readings from the light sensors. The light sensors are up here, and they record light in a unit of measurement called lux. Originally in our proposal and in our design, we were going to have the light sensors compare readings to move and rotate the angle of the solar panel system until both readings were the same. But just to avoid any problems with the system moving around too much, we decided to include a buffer of 1,000 lux.
So, for example, if this sensor was receiving a lux value of over 1,000, then this sensor, we would activate this little stepper motor right here, and it would tilt the panel to this direction in order to bring this sensor closer to the light, and works the same with this sensor. So once we get the values from the LCD, we compare it, and then activate the motor. Something that is a little bit different than our proposal is we ended up using two different I²C buses. We initially planned on only using one. However, because the sensors had the same address, we had to split it up. So this first sensor right here is using PB8 and 9 on I²C1, and this sensor is using I²C2 on PB13 and 14. This motor stand right here, we were able to 3D print with also a little gear on the back side that is able to tilt the motor. And then this stand we just made to prop up the thing. But that's basically all the hardware and how it works. Once the sensor is received, the panel activates the motor and then tilts the direction it needs in order to put the light in the center and make sure that these two sensors are reading a lux value that's within a 1,000 lux threshold.
One more thing, the driver for the motor is going to be powered by an external 5-volt source. And so the driver here is connected to the motor, and the motor is wired to the GPIO-C pins.
All right, now we're going to show you how our code works and give you a brief overview. Right here, we're in our main function, and the very first thing we're going to do is going to turn on the HSI 16 clock. This will make our program run with a clock of 16 megahertz.
And then we initialize everything. So we initialize the motor, the GPIO sensors, and we initialize the light sensors and the LCD and the I²C as well. And so with the light sensors, for that, we send the value 3 to the control register to turn on the sensor, and then we wait, and then we have a function to verify that the light sensor has been turned on. And so for our systic, we set it up to make sure that the systic handler ticks once every second by setting the ticks to 16 million.
Yep. And now that we have everything initialized, we start our while loop right here. We're going to check value 1 and value 2. We use these through the read 1 and read 2 functions in our light sensors. All this is doing is just reading the data from each light sensor. Once we read each light sensor, then we check to see if we need to turn clockwise or counterclockwise. If we need to turn clockwise, that would mean that this check clockwise value is greater than 1000 lux. We would then unwind the motor clockwise 1 tick to account for that and to tilt the panel. Same thing goes with the check counterclockwise. If counterclockwise is greater than 1000 lux, it means that we need to wind the motor counterclockwise and tilt the panel that way. After that, then we put the values into a string using the sprintf function. Then we have a short delay. This if statement right here checks if counter is 1. This counter is set by sys_tick every second. So every second, this counter will be initialized. And if it is initialized, we'll clear the LCD and then display the data of both sensors. The reason we did this is because this block up here is going constantly while our program is running. It's constantly reading the values and checking and winding the motor, but it's only going to print the values once every second. This makes sure that we can actually read the data and that it's clear, because if we have it always printing, it's pretty unreadable and we weren't able to see what the sensors were reading. So the winding and checking will go on all the time, but once every second, we'll actually print the data to the screen so that the user can read it.
All right, so here we have our solar panel system all wired and set up. And so we have here a 5 voltage source that goes through the driver and powers the motor. And then we also have an LCD screen that displays the readings of the light sensors. And now Kendall will kind of demonstrate how it all works.
So this system will be tested using my phone flashlight. I'll kind of show you how it works. Like Every said, these sensor values are being displayed once every second. And then if we shine a light on this end of the panel, it'll track that way. Same thing if we go that way, and then it'll stop once the values on the LCD are within 1000 lux of each other, meaning that the light is concentrated in the center and not dominating one end or the other. This ensures that the light is always hitting all of the panel and maximizing the amount of electricity that can be generated. So once again, if you go this way, it'll tilt there, stop once it's within 1000 lux, and same if you bring a light that way, it tilts there. This system will also work in reverse through shade. If you shade this side, it'll bring this sensor out of the shade and make sure that both sensors are always receiving a lot of light. And that's how the system works.
Thanks so much for watching our video.